Welcome to our video, We Are Orange County Drones. For our project, we decided to design and analyze a custom quadcopter. Over the past few years, quadcopters have become a viable consumer product and are used in a variety of applications. We designed iterations for our quadcopter after running a multitude of simulations. The first static simulation is to simulate a person stepping on the quadcopter with half of their weight. The following boundary conditions were used: fixed roller, fixed, and roller. The ultimate tensile strength of ABS plastic is considered to be 40 megapascals. While these results are not accurate because this material needs to be analyzed in a non-linear analysis, they still give a comparison of the various design changes. We found that the roller failed due to insufficient constraints, and the most realistic boundary condition was fixed roller. We found the maximum stress to be at the inner corner of the legs where they connect to the quadcopter. The quadcopter did not exceed the ultimate tensile strength of ABS for the 222 Newton loading. However, it did for the other two loads. We also ran a buckling simulation for a person stepping on the quadcopter. The results show that the legs will buckle after a load of over 250 Newtons is applied. These results are comparable to our closed form solution for mode 2. The second static simulation is to simulate a person kicking or pushing the side of the quadcopter. We used a fixed roller boundary condition and the quadcopter did not fail. Therefore, no new design iterations were required. Next, we ran a nonlinear simulation on the propeller hitting a wall at 1300 RPMs. The results showed that the maximum stress is 908.4 megapascals. A hand calculation was also done treating the propeller as a cantilever beam with the results of 1.089 gigapascals maximum stress. The error between these is approximately 20%. This error is likely due to the assumptions in the simplifications shown. Under both circumstances, the propeller failed. We performed a modal simulation and used soft spring constraints to simulate the quadcopter during flight. The results proved that the first 6 modes are due to rigid body motion as expected. The other modes must be avoided by the components to avoid resonance. We used a transient thermal simulation to analyze the effects of heat transfer from the motor to the arm during 10 minutes of use at maximum power. The glass transition temperature was not reached. We also performed a thermal stress analysis, but the stresses were negligible because ABS has a low thermal expansion coefficient. We performed a nonlinear explicit dynamic simulation using ANSYS Mechanical 17.1 to analyze the maximum stress and factor of safety of a crash landing. The analysis covered 1 millisecond of real time using 30,000 elements and took 2 hours to run. The impact destroyed the drone with a minimum factor of safety of about 0.03 and a maximum stress of 466 gigapascals. SOLIDWORKS does not allow fatigue analysis for nonlinear materials. The SN graph for ABS is shown. Based on these simulations, we concluded that the landing gear needed to be redesigned. The first iteration added fillets with the intent of reducing the maximum stress at the connection to the base. The iteration slightly reduced the max stress for all 3 loads. However, only the 222 Newton load did not fail. The max stress was transferred to the base plate. The next iteration connected the base of the initial landing gear and performed better than the last 2 design changes. For all 3 loads, our max stress did not reach the ultimate strength of 40 megapascals. This design iteration increased rigidity in the landing gear, which appeared to distribute the load. This concludes our video. Thank you for watching.